I want to look at drawing the graphs of derivatives, because a derivative, the slope of a function, oftentimes is a function itself, or the slope of an equation is an equation itself. So a lot of times you can draw a graph of all the different slopes on another graph. Sounds mind-blowing. It's not that deep. Here's a graph I just randomly drew up there. We can call it f of x, g of x, h of x, p of x, r of x, whatever. I picked out 3 points. How can you find the slope at just those individual 3 points? Here's one way. Well, how about that? If you want the slope at individual points, literally draw in the tangent line and then just find the slope. I'm looking at this one going, well, if we started at this point, we went up 1, 2, 3, 4, 5. We went across 3. I bet the slope right there is 5/3, positive. This one, when I see, I'm picking out 2 points that are really easy, but it looks like it went down 1 and went over 5. So the slope at that point, x2, is negative 1/5. And then the slope up here of a horizontal line is 0. So you can find the slopes of those individual points. What I want to be talking about is how do you get the slope of the entire graph? And, really one of the things is you're just going to estimate for a lot of these. You're just going to try and use some common sense and put some things together. Let's start off easy. What if you have a linear function? Well, it turns out linear functions are pretty nice. Let's look at this one. It looks like, well, it goes up 2 and over 1, then up 2 and over 1. The great thing about linear functions is the slope's always the same. And for this, the slope at every point on that graph is a slope of 2. So guess what the derivative of my function would be? The entire derivative is going to be a value of 2. Likewise over here, if my slope is negative 1/2, my derivative for g, wow, okay, I tried to do it correctly. If it's not exactly a negative 1/2, I'm sorry, but yeah, every single point is at negative 1/2. So when you have linear functions, you just check and see what the slope is at every point on the green original function. And whatever that slope is, that's what number you put in for the actual derivative. If your graph is made up of several lines, like a piecewise function, you've got all kinds of line pieces, parts of lines, like the absolute value function. Well, you're still just going to take a look and say, well, this part that's a line has a slope of negative 1. So every point on that derivative right there is going to be negative 1. And every point over here is positive 1. So this derivative here is positive 1. What happens at the point in the middle? Well, remember, at the pointy bits, it is not differentiable. So I'm going to have an open circle here. My derivative is really made up of 2 numbers. It's always negative 1 until we hit that vertex, and then it's always positive 1 afterwards. Likewise, for the piecewise function over here, this part had a slope of 1, that part had a slope of 0, this part has a slope of negative 1. Notice at any of the corners or anywhere where it is not continuous, there will not be a derivative there, which is great for lines again. Now curves are where this gets a little harder and you can't be precise at every point. That's okay, I just want a general sketch.